question. Okay. Just as we were trying to do in the previous class. Okay. So from the last class, if you remember, from the last class, we talked about the um, practicals that we do in WIEC chemistry, and we mentioned qualitative and quantitative analysis. Okay, so the qualitative analysis is the one that has to do with checking the quality of a particular reagent or a particular chemical. Okay, so in that kind of practical, we will be told, given some information about a particular reagent, we will test for it, and we would check for, we'll check qualitatively by observation. So we can observe things like solubility, we can observe things like color change, we can observe things like smell, okay, those physical things that can tell about the quality of a particular chemical. And then we have quantitative analysis. That is the one, as the word implies, it tells us the quantity. Quantity would have to deal with number, right? So that is the one that we get to deal with number. And usually for this kind of analysis, we deal with titration. Okay, and it could be acid-base titration or redox titration. Redox titration is reduction, oxidation, titration. Okay. Now, for titration process, I already explained some aspects of it from the previous class. Okay. And when you told me that you have not done the practical before. But in essence, what actually happens in a titration experiment is, okay, rather than me saying that, does any of you remember the steps or the processes we talked about in the titration process from the last class? Or at least if you can mention some tools that will make use of in titration experiment.
Burette,
A burette, yes.
Kronecker flask,
A conical flask, yes. Okay, we have so many like that. Okay, and to
Pipette.
yes, a pipette. And to reiterate, wait, let me ask. Have you all done a titration experiments before?
yes,
Okay, you have. So I assume if Uyosa has, then the rest of you have, right? So we can go on to talk about just the calculations because you already know the steps involved in the process, right? Am I right? I want response from everyone.
yes. Yeah.
Okay. So that is to say, since we already have carried out a titration experiment before, that means we know that in a titration setup, in our burette, like this, for example, okay, our burette contains the titrant. Okay, because in our experiment we'll usually be given instructions just as we see in this our question paper on the screen. We'll be given instructions, we'll be given details. Okay, and when we are watching out for our detail, for example, okay, let's read from the beginning. You say all your burette reading, initial and final, as well as the size of your pipette must be recorded. Okay, but no account of experimental procedure is required. All calculations must be done in this booklet. This is 2024 SSC. Now D contains 4.3 gram of nitric acid in 500 centimeters cube of solution. Okay, and then E is prepared by dissolving this gram of washing soda crystals, okay, in these centimeters in 250 centimeters cube of distilled water. Now, these are like introduction to your reagents that you're going to be using. So we have HNO3 and sodium 2CO3. That is washing soda crystal. Okay. Now the first step is put D into the burette and titrate it against 20 or 25 centimeters cube portion of E. That is to say, our titrant is going to be our D, right? That is what we're going to put in the burette. And then uh, that is our acid is what is going to the burette, and our base, our washing soda crystals, is what is going to be acting as our base. Okay. And then we'll repeat the exercise to obtain concordant titer. Do you know what concordant titer is? Concordant titer is the values we get, is when the values we get from the burettes when we have taken first reading, second reading, you know, the values when you know that when we are doing a titration experiment. We have a table, for example, like this, and we have our initial reading. So we have initial. Sometimes some persons will be in the column or in the row. It just depends on you. We have initial and then we have final. Now we have and then we'll have our rough if necessary. Then we have our first reading, second reading, third reading. So when we have something like this, when we have something like this, we can say, for example, after carrying out our first experiment process, we got our reading from our burette to be 21. Okay. And then our final reading is 21. Then our initial reading was 0 for the first reading. So let's just say the first reading is for our rough. Okay. For our rough, the initial is 0 and the final is 21, for example. And then for our first actual reading, the initial is 21, for example, and our final is 43. Now the difference between 21 and 43 is 22. So that is to say the difference between our first reading, which is our rough, and this next reading is 22. Um, the difference is 2 rather, because this is 22 and this, okay. We'll find the difference. The difference here is 21 and this is 22. Okay, so the difference between the rough and the first reading is 2, which is too big. Now the concordant titer value is telling us that the difference between um two readings that you're going to be using should be not more than 0.2 centimeters cube. So having a difference of 2 is so much. So concordant titer value have to have um closeness in value or some level of similarity. Okay, that accounts for accuracy to an extent. Are you all understanding me?
Yes, ma'am.
Okay. So that is what they mean by repeated to obtain concordant titer. Now, so we are going to, since we are not actually, we didn't actually carry out any titration process here. For these first parts, we're asked to tabulate our result and calculate the average volume. That's the essence of the whole titration process. Not only to get our endpoint, but also to get our volume of whatever the titrant is. That is whatever what is in the burette is. So we want to get the volume of that thing. Okay. So we're going to be formulating some readings here. uh, since this is an online class and we didn't carry out any titration process exactly. So to be able to solve this question, please pardon my bent line. Okay, first off, we have our rough. We have our first reading, our second reading, and our third reading. Okay, and here we have our initial. Also, okay, before then, let me just finish this one. Final, and then we have our titer. Okay, also, you should write your units so that you'll be given an accurate report. Okay, this is in centimeters cube, and our titer in centimeters cube. Okay, everything just setting. So this titer, it just means the difference between the initial and the final. Okay. So for our rough, when we have filled our burette to a zero point zero point, so we are starting with a 0.0. And so let us assume our final reading would be 24.8. Okay, so for our second reading, let us assume it's 0.0. Let us just start everything from a zero base. Okay, 0.0. And then for the second final, let us say we have 24.60, and the next one we have 24.70, and the next we have 24.60 again. So our final titer, the difference between initial and final, will be likely the same number. Okay, it's when maybe your initial reading, you did not fill back your burettes. Maybe your initial reading will be, maybe for our first titer, our initial reading we continue from 24.80. Then our final reading will now be maybe 48 point something. You will now find the difference between them to get the tighter reading. So that is what it's sometimes, or it's usually advisable to fill back to 0, just for increased chance of um kind of accuracies or something like that. But it really doesn't matter if you don't fill back. But at least after at least two rounds, you should fill back. Okay, so let's assume we're taking these readings. Now, if you notice, the difference between each of our titers is not more than a 0.2. Okay, that is what shows you accuracy in your reading. When you're having readings that have up to one difference, one is 24, the other one is 25, it's not good for you. Okay, so what I wanted to say before, you said all period reading initial value as well as the size of your pipette must be recorded. Okay, so you can also have information of this. Ensure you have information of this written, but no account of experimental procedure is required. Okay, so if they said put D into burette and titrate, so you can they are pipettes. They are pipettes of 20 centimeters cube or 25 centimeters cube. You should take notes, put down the pipettes that your school is using. It's the pipettes that we use to get our analytes, which is what in this case the base is, which is what the E is. Okay, so we have to note down which of the pipettes you use. Okay, and then um we are to calculate our average volume. Now, to calculate our average volume, we do not need to include our rough. Okay, and also let us assume that our third reading was something like 25 25.6. This is too big. The difference between this one and the second titer is too big. So if we want to now find our volume, we don't need to really add or include this third titer. We can find our average volume by just adding up the second, that is the first reading, the first titer, which is this one here, and the second one. We'll find the average of the two of them like that. Okay, rather than including a titer that is not a concordant value. Okay, so but for this case, that's not the case. So it's always advisable to make everybody no more than 0.2 difference. Now our average volume would now be equals to 24.60 plus 24.70 plus 24.60. We're not including the rough, right? Divided by 3. So this will be equals to 24.63 by the time we add up and divide. Always remember to include your units. I hope everyone is following. If anyone is confused, please let me know. If you have questions at this point, ask the question now. So that, because as we progress, it might get more complicated, probably. So that we don't go too much backward and everything doesn't look strange to you again. So if you are not understanding up to this point, or if you have a question at this level, you ask now. Okay, I assume everyone understands. Now we are done with this first question. The next is write a balanced chemical equation for the reaction. A balanced chemical equation for the reaction. Now, when we go back, we see something here. We see that this is an acid-base process. Okay, our acid is HNO3, and our base, yeah, we're taking it to be sodium to tricarbonate. Sodium tricarbonate. Okay, so that's what we're going to be taking these as our base. So this base, if you look at it, is hydrated. That is why we see this XH2O. Okay, so we really don't need to include that in our balanced equation. We just have to include what is standing there as our base. So to write our balanced equation, we have our acid HNO3. Please, I hope you can see the screen at this point, because this bottom part is kind of dark. Can you all see my screen?
Yes, ma'am.
Okay. So we have HNO3 reacting with our base, which is our sodium tricarbonate. We know when these two react, we'll get salt and water. But then again, if you remember when we were dealing with acids and base, probably I mentioned it, or likely I mentioned it. When we're dealing with acids and base, um, when acids react with carbonates, okay, or metal carbonates, bases that are metal carbonates, we don't only get salt and water, but we also get carbon dioxide gas involved in the process, okay? So that is to say, when the base is not something like sodium hydroxide, that will be forming just salt and water. When there is a carbonate, tricarbonate in the base, we'll get a carbonate in our balance equation that will be involved in the process where our salt and water is being formed. Okay, so from here, first off, we get our salt, positive side being donated by our base, which is the sodium, okay, and the negative ion being donated by our acid, okay, which is the NO3 ion, okay, and so that's our salt, then our H2O, and then carbon dioxide, because it's a carbonate that's acting as a base. Now the next thing is to balance it. Our equation is not balanced yet. Our hydrogen in the reactant is 1, in product is 2, so we have to make it 2 in the reactant, okay? And then our NO3 is 1 in the reactant. We're going to be treating NO3 as a single unit, okay? So this is like an ion on its own, because the way it is combined and packed together in the reactant, that is how it is together in the product. So we don't have to be saying N is 1 in the reactant and N is 1 in the product. Oxygen is this in the reactant. So we are treating them together. So they're acting as a single unit. So NO3 in the reactant is 2, and NO3 in the product um is 1. We have to make the product also 2. So put down 2 here. Remember, I'm not going to alter the subscripts. It's the coefficient, the big number at the front, that um affecting. Because altering the subscripts is changing the whole formula. And then the next is sodium. Sodium in reactant is 2, and also 2 in the product. And CO3. CO3 now is actually splitted in the product, so we will not treat it as a single unit, unlike NO3, okay? So we have 1 carbon in the reactant and also 1 carbon in the product. Then we have 3 oxygen in the reactant, then 3 oxygen in the product, formed from 1 oxygen from H2O and 2 oxygen from CO2. Do you understand? So this will be our balanced equation. Now, the next question is, okay, if you understand. Now, the next question is, from the result and information given, calculate the concentration of E in mole per dm cube. Concentration of E. Now, if you notice, E, okay, we are going to be looking for the concentration of E in mole per dm cube. The first thing, when you see questions like this, the first thing that we would ask ourselves is, what is the formula that we are going to be using in this kind of situation, okay? Now, when we see something like finding concentration in mole per dm cube, there are different formulas you should take note of at this level. I believe I wrote them before in the previous class, but let me also note them down again. Let me bring my book. So now, some formulas we should be having at the back of our minds when we are dealing with titration process is one, we should know that number of mole is equals to mass divided by molar mass. Another formula we should be taking note of is also, again, number of mole. Another formula for it is equals to concentration times volume. Also take note of your units, when you should convert and when you should not. Okay. And also another kind of more jam-packed formula is when we are dealing with comparing to comparing between the acid and base, for example. So we can have number of mole for one divided by number of mole of the other is equals to concentration for one, volume of one, concentration of the other, volume of the other. More formulas we should take note of is formula for molar concentration. Okay, molar concentration, the unit for it is mole per dm cube. Now, molar concentration is given to be equals to mass concentration, which is measured in gram per dm cube, divided by molar mass. Now, another formula we can take note of is that mass concentration, we can derive formula for mass concentration from this molar concentration. But other than that, we should also know that mass concentration is equals to mass divided by volume. Okay, remember this mass concentration is in gram per dm cube. Then also molarity, which can also stand as concentration, okay, also implies it is equals to moles divided by volume. So these are some or the major formulas we need to keep in mind. So let's go back to our question. Or is anyone writing it down, or the group vibe? You're familiar with these formulas already. So sometimes when you see some certain questions, you ask yourself which of these formulas will favor me, would work for this question. Okay. Now, if we are dealing with the concentration, if we are dealing with the concentration of E, now we'll go back. Let us see what E is. E is our base, NO3, right? I said NO3, N2CO3. So the concentration of this and what information of that N2CO3 we're given. We're given its volume and we're also given its mass. Okay, so how do we get the concentration? First of all, since we are told to find the concentration in mole per dm cube, okay, we're going to be using this formula, mass concentration divided by molar mass. But from our question here, we're not giving mass concentration. Okay, so the first thing that we can do to answer this question, we're not giving the value for mass concentration. Okay, so how about we now use the formula moles divided by volume? That also would not work. So what we can easily do here is to first of all find the concentration of our acid. Okay, because we're given the mass of acid and also the volume. So since our mass of acid is equals to 6.3 gram, going forth and back is so much, but I believe you already saw it initially. Okay, this is the mass of our volume and that of our mass and volume of our acid. Okay, so we have the mass to be this, and then to get the concentration of it, remember C is equals to number of mole divided by volume. So we'll have to first get the number of mole, and we know that number of mole is equal to mass divided by molar mass. So the mass is 6.3, and then the molar mass of our acid, we're dealing with the acid now, which is HNO3. Hydrogen is 1, molar mass of hydrogen is 1, plus that of nitrogen is 14 in the periodic table, so the molar mass of, nitrogen is 7, so the molar mass is going to be 14, and oxygen is 16, so 16 times 3, that's going to be giving us 16 times 3. I hope you all are with your calculator. You can also be helping out with giving the values. So 3 times 6, that will be 18. 3 times 3, 4, 48. So when we add all these up together, is 63 gram per mole. Okay, so we have 63. So 6.3 divided by 63, we have 0.10 mole. This is the mole for our acid. Now we can now get the concentration for our acid. To get the concentration for our acid, we need this number of mole, okay, which is equals to 0.10 divided by the volume that was given to us. Remember, the volume that is given to us is 500 centimeters cube. Okay, but then again, you see that they were asked to find our concentration to be in mole per dm cube. So this, if we are going to be using that 500, it means that our concentration is going to be in mole per centimeters cube. Okay, so we have to be in unity with, or in uniformism with our units. Okay, so we'll be converting the 500 centimeters cube to dm cube. Remember I said 1000 centimeters cube is equals to 1 dm cube, or 1 liter. Okay, so when we are converting that 500, we have 0.5. Okay, so this divide 0.1 divided by 0.5, 0.20 mole per dm cube. Now this is for our acid. We were asked to look for that of the base, which is E. Now we need this information from the acid to be able to get that of the base. Okay. Now, based on our balanced equation, we see that we need, we will actually be using the formula C, concentration of acid, times volume of acid divided by concentration of base times volume of base, equals to number of mole of acid divided by number of mole of base. This is the formula we'll be using. Okay. Now we have gotten the concentration of our acid. Okay, our concentration of acid is this one that we got here. So Ca is equals to 0.20. Now how about the volume of our acid? The volume of our acid is not going to be this 500 here. This is the volume of the solution, that is acid in a solution. But the volume of our acid, okay, is going to be this titration value of just the acid, not the acid in a solution. Okay, so our volume of acid is going to be, what did we get? Okay, 24.63 centimeters cube. Okay, so we're going to be writing it 24.63 centimeters cube is more dm cube. Okay, then our concentration of base, we don't know. That's what we're going to be calculating. And then our volume of base. Okay, what will be our volume of base? When we come back here, we would see that we pipetted 25. Okay, let's assume we are going to be using 25 pipettes, 25 centimeters cube pipette. So that will be the volume of our base. Okay, so volume of our base is, that's the volume of E, is going to be 25 centimeters cube. Okay, now the number of mole based on the balanced equation. Okay, we can see that based on the balanced equation, we require 2 acid for 1 sodium tricarbonate. So we're going to be taking the number of mole of acid, Na, to be 2, and that of base is going to be 1. So we'll be working with the coefficient. So from here we can get our number of mole. Rather, from here we can get our concentration. Now you may ask, why don't we use this number of mole here, 0.10? If we do use this, we're also it's like the ratio is already 2:1. So we're still going to be using, it's going to be the same ratio. So what matters is the ratio difference between them. Okay, so when we fix this all into the equation, we're going to be having that is 0.20 times 24.63 divided by what we don't know times 25, that is the volume of the pipette we used, is equals to number of mole of acid, which is 2 divided by 1. Okay, so when we calculate this and cross multiply, then tell me your answer. Yes, what's your answer? Is anyone calculating?
0.01.
0.01. Are you sure it's 0.01?
Sorry, 0.09.
Okay, 0.09.
0.98.
Okay. So we have 0.098 mole per dm cube. Okay. So this is what we will get when we look for the concentration of our base. So we can see that what are the formulas we use here? We use the concentration equals to number of mole over volume. Okay, so at the end of the day, when we are looking for concentration of one of the unknown, okay, it's best advised to use this formula. And we'll see things like mass concentration and the rest can make use of these others. So it's not a complex process. We just have to first look for the concentration of those ones that are being given to us, especially of the acid where we get the volume and every that way we got the calculated volume. Okay, and then we will now get the concentration of what we do not know. Please, if you don't understand, let me know. Now the next question says, what is the value of x in this? Okay, in the sample E. Now to get the value of S, we saw in the initial question here that we are dealing with, for E, we have this mass of it, of the whole hydrated solution, okay? So we have 8.2 gram of it that is being dissolved in 250 centimeters cube of distilled water. Okay, so the first thing that we are going to be doing, and we also another information we also know is the concentration of sodium tricarbonate. So we would first look for the moles, and then we would know the molar mass of everything here, and then we would now subtract the molar mass of the base itself without being hydrated. Okay, so let's go. So first off, we're going to look for the moles in 250 centimeters cube. The moles is going to be our concentration that we just calculated, okay, which is 0.098 times our volume, which is 250 centimeters cube. But remember that this 0.098 is a mole per dm cube, and our volume is in centimeters cube. There's contradiction here. So for unity's sake, we're going to be converting our volume. Okay, our volume will now be 0.25250, just 25. So we'll multiply this, we'll have our number of moles to be 0.0246 moles. Okay, because the centimeters cube cancel out the other centimeters cube. Now we are left with the unit mole. Now this is the number of mole, okay, for this whole thing here. Okay, and then also we know that, so since we've gotten the number of mole, we can now get the molar mass. We get the molar mass, and since we know the mass to be 8.20, it will be, we know that number of moles equals to mass over molar mass. So molar mass will be mass divided by number of moles. The number of moles is 0.0246. So our molar mass is 333.3. So why are we going through all this process? For us to be able to know the value of X, we have to know the molar mass so that we'll know what number we'll attribute to X. Okay? So that is, we have to know the molar mass. And the molar mass, for us to know the molar mass, we need mass and number of mole. Okay? Mass has already been given us in the question. But number of moles, we don't know it because we can't use the number of mole. This number of mole that we calculated here, that we got here, is that of just sodium tricarbonate, not the hydrated form, not E, the sample E that has crystals, that has H2O attached to it. Okay, so that's why we need to use the information in the initial question to get the number of moles separately, which will help us get the molar mass. Now, since we've gotten our molar mass and we already know the molar mass of sodium tricarbonate, we have 333.3 minus the molar mass of sodium tricarbonate. Okay, we didn't calculate it here. Okay, molar mass of sodium tricarbonate, we have 2 sodiums and 1 sodium is 23, so that's 26, plus carbon is 12, plus oxygen is 48, like we calculated earlier. So the molar mass of sodium tricarbonate is 106. So we have 106. So when we subtract this, we have 227.3. So that is to say, only this hydrated form, this XH2O, has the that is going to be occupying this 227.3. Okay, that's the water part. The H2O part is this 227.3. Because what we subtracted is just the tricarbonate part from the O molar mass. Okay, so what we are going to be doing to know what X is now going to be, we know that the molar mass of H2O, of water alone, is 18. This X here tells us the number that goes with both H and oxygen. So to find our X, it's going to be this molar mass that is covering everything. This molar mass that is meant for the hydrated, for the water, divided by the molar mass of just H2O, the simplest form of it. So we have 18. Okay, when we divide this, we have 12.6. So that is to say, X is approximately 12. That is to say, when we are to write this formula, this E, we'll write it like this: dot 12H2O. Okay, do you all understand? Please, if you understand up to this point, let me see. If you don't understand, also let me know. Golden, Uyi, Melody, Christine, do you all understand? Winner is not in the class today.
Yes, ma'am.
So the most thing about this whole titration topic and calculation is understanding what is really going on and the information given to you. Don't mistake one information for the other. It's just like mistaking 8.2 grams to be the mass of the base. It is the mass of the base that is dissolved in water. That is the hydrated one. So we can't use it when we are talking about just the acid and the base. So there are different things we have to have understanding of, the process and the steps. So Please, if you have a question, you can ask now. So I'm assuming there is no question. All right, since there is no question, okay, let's call it a ninth. We would continue this particular here. That's not all the question, but that's most of the main parts. In fact, that's the most of the part for this titration aspects. This first titration aspects. Okay, that's, at the end of the day, the aim of titration is to get our values for volume and to be able to use to calculate unknown concentration. That's the aim. Okay, so that is what we have achieved in that first question. So in the next class, we'll go ahead with the second and third question for that year. I hope you all learned something today. Hello, I hope you all learned something today.
Yes, ma'am.
All right. Okay, that will be all for today. See you in our next class.
Thank you, ma'am.
Bye bye. After I don't do click, click, click.